Okay, good afternoon everybody. We are here today to hear the latest results on the search for the Higgs boson from the two big experiments from ATLAS and from CMS. The seminar is arranged like this, that we start first with the ATLAS presentation by Fabiola Gianotti, and then by the CMS, and then we continue with the CMS presentation by Guido Tonelli. Questions will only be at the end of both presentations. That makes much more sense. I will guide you through the questions, but before we start now, I think it's now the time to say why we can be here, namely because there was a fantastic performance, not only of the experiments, but also of the LHC and the whole accelerator complex. So I think all the people who are involved and who have been involved and are involved in running this thing, building this thing, running this thing, having such a big success, I think they deserve a big round of applause, please. Okay, thank you very much. I know that you would have continued for half an hour, but we are running out of time otherwise. So I pass the micro to Fabiola, please.
Thank you. Okay. So good afternoon, everybody. It's a big honor, and I will say also a big emotion with all these people to be here today and to present updated results of standard model Higgs searches on behalf of the ATLAS collaboration. So this slide summarizes our results. These plots shows the reconstructed mass spectra for the 11 distinct channels in which we have been studying Higgs decays, and we have been searching for the Higgs bosons. The data are compared with the Monte Carlo expectation for the background, the white histograms, and the expectation for various signals in red of various masses. In some cases, the signals are scaled up by some factor, but not always. So I think it's quite remarkable that we are at this stage today, because I would like to remind you that Higgs searches are among the most difficult and demanding channels at the LHC. And so for these reasons, and of course also because Higgs is a primary goal of the LHC, they've guided the conception, design, and technological choices of the ATLAS and CMS experiments, setting very stringent requirements on the performance in terms of lepton identification, lepton energy scale and resolution, bit tagging, missing energy, jet reconstruction in the forward and central region, etc. And I remember a very enriching discussion on the beginning of the 90s with some of my CMS friends about comparing the ATLAS liquid argon and the CMS crystal calorimeter for X to gamma gamma. So today we'll see some follow-up for that discussion. So past studies have assumed a lot of luminosity and very high energy, as you can see from this historical figure from the proceedings of the Aachen workshop, the LHC Aachen workshop in 1990. But today, after essentially only 2 years of LHC operation, ATLAS has achieved excellent sensitivity over a large part of the allowed mass range, thanks to several ingredients. First of all, the outstanding LHC performance, a detector operational efficiency and data quality close to 100%, excellent detector performance, and a mature understanding of it, which is reflected in detailed modeling of several subtle effects in our simulation, and a huge number of physics studies based on the data recorded in 2011 and 10, which have allowed us to measure the main standard model processes and many backgrounds to Higgs searches. So I will say that the work of building solid foundation for the difficult Higgs searches is well advanced. So let's start for the data. So in 2011, the LHC has delivered to ATLAS 5.6 inverse femtobarn, and I would like to echo what the DG just said. The ATLAS is extremely grateful to all the people who have conceived, built, and now operate the LHC for this extraordinary performance. Now, some of the processes that we are going to study, like for instance X24 lepton decays, are extremely rare. So it's very important that we use every single small bit of this integrated luminosity that we try to do with a data taking efficiency which is larger than 90%, 93.5%, with a fraction of non-operational channels between a few per mil and a few percent. These are very complex detectors, so it is quite remarkable. And a good quality data fraction they used for the analysis between 90 and 96%. Now, the peak luminosity seen by Atlas in 2011 has achieved 3.6 times 10 to the 33, and the price to pay for the high luminosity is high pileup. That is a high number of simultaneous proton-proton interaction per bunch crossing. And this pileup has been increasing during the year. It was typically, on average, 6 events per crossing until the end of August, but then the machine changes the optics. They moved to narrower, to more squeezed beams, and so the average pileup went up to 12 events per crossing on average, with tails extending up to beyond 20 events per crossing. So here you can see a spectacular event that we recorded in September. You see the production of a Z going into 2 muons, together with another 19 vertices coming from several soft interactions in the same bunch crossing. So today we are actually operating in much harsher conditions that would have been expected at this stage. I remind you that the scenario with which we have been making all our estimation over the last 20 years assumed 20 interactions per crossing when running at design luminosity 10 to the 34. And clearly these conditions are challenging in terms of trigger, computing resources, reconstruction of the physics object, especially quantities integrated over the full detector like missing energy, or very soft objects like soft jets. So a precise modeling of pileup in the simulation is essential. So clearly, at a Hadron Collider operating in such an extreme conditions, the performance of the trigger is demanding, and is also crucial in order to capture as much as possible of the interesting physics. So our trigger has been coping very well with the rapidly increasing luminosity through very smooth and flexible changes of the prescales, thresholds, and menus, while keeping very good efficiency for physics, especially at low PT, because this is again important for Higgs searches. As you can see, we have been running with a typical output rate to storage of 400 Hertz. Here you see one of the fields taken at very high luminosity, equally shared among the mainstreams, E gamma, jet tau, ETMIS, and muons. And what is also important is that we have managed to keep relatively low thresholds on leptons that are again critical for many physics studies, in particular Higgs searches, at the level of 18 to 22 GeV for muons and electrons, so low PT, but also quite stable in the course of the year. This main menu is complemented by a very rich palette of supporting triggers. For instance, we have been recording a special JPSI2EE stream for unbiased studies of low PT electrons, which turn out to be extremely important for instance, X24 electron studies. So moving now to physics, of course, measuring the standard model at 7 TeV has been the first milestone of the LHC program, important on its own, but also because the standard model processes are, of course, backgrounds to many searches. So this plot summarizes our present measurements of many cross-sections, inclusive W and Z, TT bar, single top, die bosons. And we can conclude essentially 3 things. First of all, the standard model works at 7 TeV, which is very good, and be extracted from the huge QCD backgrounds in a convincing way. So the experimentally most sensitive channels in a very oversimplified pictures are indicated here as a function of the Higgs mass. Gamma gamma is the most sensitive channel at low mass below 130 GeV. X2WW to 2 leptons neutrinos and X24 leptons through a ZZ pair are the most important channels in the low intermediate mass range, and X2ZZ LL nu dominates at high masses, at large masses. I would like to note that huge efforts have been made over the last months by our friends theorists to compute the Higgs production cross-sections to next to leading order in most cases, thereby reducing the theoretical uncertainty to below 20%. And there's been a lot of progress also to improve the understanding of and the prediction of numerous and complex backgrounds to next to leading order in many cases. And we are having very fruitful discussion with them. So this slide summarizes the present status of Higgs searches, at least as of now. So you can you can see in this plot, which will be shown later on at least 100 times between myself and Guido, the ratio between the cross-section excluded at the 95% confidence level and the standard model cross-section as a function of the Higgs mass. The points here are the results of the first combination of the ATLAS and CMS data based on the integrated luminosity recorded until end of August, up to 2.3 inverse femtobarn per experiment. Compare with the expectation, the dashed line, in the case of background only, with the 1 sigma and 2 sigma bands in green and yellow. This color code will remain also in the rest of the presentations. So the region below 1 is excluded under 95% confidence level. So this is this orange region here, which go from 141 to 476 GeV, and the large part of this region is excluded at the 99% confidence level. So you can see how quickly the LHC was able to explore and constrain a large portion of the previously allowed mass range. I would like to stress that this combination is not a trivial exercise. It requires harmonization of the inputs of the two experiments. It requires a lot of details and subtle effects related to the way systematics are treated, and therefore it's a very good example of cooperation, early cooperation between the two experiments. Now, the region, the low end of this part of this mass range is still excluded by LEP with a lower limit 114.4 GeV, and it will be so for another 10 minutes. So today, essentially, the region where we are going to focus, the most interesting region, the hottest region, both experimentally because of the exclusion and 95% confidence level, but also because best motivated by the theory, by the electroweak fit, is the region between 114.4 and 141, and this is the region on which I'm going to focus in the rest of this presentation. So over the last months, we have made huge efforts to improve our understanding of the detector performance, particularly of this latest period of data taking affected by a higher pile-up, as you have seen before. And also, we have benefited from the increased statistics of the data recorded this year to really start to dismantle the systematics uncertainty, given that most of the measurements are now dominated by this. And the resulting improved knowledge has been propagated to our simulation, our reconstruction. For instance, we have new alignment of the inner detector and the muon spectrometer. We have a better simulation of the absorber plates in the calorimeter, which gives a better agreement in the shower shape between Monte Carlo and data, and so better agreement in electron and photon identification. We have modeled pile-up in great details, including the detailed structure of the bunch train and the in-time and out-of-time pile-up effect. So this work is a lot of fundamental work. For us is very crucial and is high priority work for the full ATLAS physics program in 2011, not only Higgs searches, of course. So concerning Higgs searches, we have updated the most sensitive channels in this hot, best motivated mass region. These are X2 gamma gamma, X2 for lepton, and X2 WW to lepton and neutrinos. To the full statistics, only the first two, because gamma gamma and leptons are the least sensitive objects to pile-up effects. So this table summarizes for the various channels that we have studied their main features, the mass range in which they were studied, integrated luminosity, the main backgrounds, the number of signal events and the signal to background ratio after cuts, and the expected sensitivity. So I will not go through. But I will only note that our results are based on cut-based selection, which are conservative, very solid, and the large and sometimes not well-known backgrounds have been estimated mostly with data-driven techniques using background-enriched signal-free control regions. So, as I mentioned, I will now focus on these three channels, X2WW, X2 gamma gamma, and X2 for leptons, which, as you see, drive the sensitivity in the low mass region. So starting with X2WW, this is potentially the channel with the highest sensitivity in the mass region between 125 and 180 because of the larger cross-section compared to what you will see later, 200 femtobar, and the relatively good signal-to-background ratio, 0.5 or so, 50%. However, because there are two neutrinos in the final states, it's not possible to reconstruct a narrow mass peak, but a potential signal will manifest itself as just an excess of events in a sample containing two leptons and missing energy on top of huge backgrounds like top production and W pair production. So the crucial experimental issue for this channel is to be able to measure this background well enough to be able to extract a convincing signal. And we do this by using control regions in the data. We cannot rely just on the Monte Carlo, especially at this early stage of the experiment. So we use control regions in the data where enrich in the given background flavor that you want to measure, where the signal contamination is small. Then we compare the data with the Monte Carlo in this control region. We normalize the Monte Carlo to the data if needed, and then we use the Monte Carlo to extrapolate the contamination of the background to the signal region. So this table shows an example of three control regions used to determine the background to X2WW searches, and you can see that the Monte Carlo expectation and the data observation are really compatible, so no scaling is needed. And this, of course, also is a demonstration that the fundamental work done in measuring and understanding the standard model process paid dividends. So another crucial issue for this channel is the measurement of missing energy, because a bad measurement of missing energy could create spurious signals. So this plot shows the missing energy spectrum that we measure at the pre-selection of the analysis. Is made by selecting events simply containing a muon pair and looking at the missing energy. And you can see that we understand the data, in particular the contributions of the various physics processes over 5 orders of magnitude. You see that at low missing energy, we are dominated by Z plus jets, where missing energy comes either from neutrinos, so it's genuine, or from fakes, jets faking mismeasured due to instrumental effects. But you also see that around 50 GeV, we clearly see the turn on of the top contribution, where there missing energy comes mainly from genuine neutrinos, genuine sources, physics sources. So you see that we understand the spectrum quite well, and because missing energy is very much affected by pile-up, we have decided to include the latest part of our data, those recorded with IR pile-up, only when we are confident that we can understand those data at the same level as we understand this part of our data sample. So with 2 inverse femtobarn, we observe 94 events in the data, to be compared with the Monte Carlo expectation, which is 1.5 sigma below, so similar. And then, if you look at the transverse mass spectrum of the dilepton neutrino system at the end of the analysis, shown here, you can see, of course, the data and the Monte Carlo prediction for the background, but you can also appreciate how broad potential signals of mass 130 GeV, 150 GeV would manifest in these channels compared to the much narrower peak we will see later on. So interpreting these results in terms of exclusion, we are not able to improve with this channel alone and with this luminosity the exclusion already provided by the Atlas plus CMS combination. One can look at what we observe here, you see, is that our observed limit, here the data points, are always within 2 sigma of the expected limit in case of the absence of a signal. And you can see, for instance, also in this 2 sigma compatibility, also in this plot, so-called P0 plot, is another kind of plot you will see many times today, which essentially gives you the consistency of the data with the background-only expectation. You see that the data fluctuates at a level of 1.5 or well below 2 sigma. In contrast, if we had a standard model X of mass, say, between 150 and 170 GeV, you see it will give a huge deviation from the background-only expectations. Of course, we don't observe such a signal in the data, and these masses have been excluded. But you see that in the low mass region here, where our observation at the level of 1.5 sigma or so, the expectation of the standard model background is very similar because the sensitivity here is lower. So today we cannot say in our data if what we observe is background only or background plus signal, because the data are equally compatible with both. So X2 gamma gamma is a completely different channel. Smaller cross-section because the branching fraction is at the level of per mil. But simple final states. 2 IPT isolated photons. We cut at 40 and 25 GeV on the two photons. In reality, the analysis is more complex because we divide our data samples in 9 categories in order to increase the sensitivity depending on the rapidity of the photon, whether it's converted or not, depending also on the PT of the gamma-gamma system, etc. So in this channel, the crucial experimental aspects are quite different compared to the previous channel. First of all, one needs an excellent gamma-gamma mass resolution to be able to observe a possible signal as a narrow peak on top of a huge background, which is a continuum, a smooth background, dominated by the reducible gamma-gamma production, and also powerful gamma jet separation capability to suppress the potential background coming from jet faking photons. So I will spend a few minutes on these two crucial experimental issues for the observation of a possible channel in this, the possible signal in this channel. So this table summarizes for a Higgs mass of 120 GeV the expected mass resolution. Overall, it is 1.7 GeV, and it deteriorates to 2.3 for 10% of the most dirty events, those that have one converted photon and the other one very near to the transition between the barrel and the end cap calorimeter. You also see that the mass spectrum and the mass resolution are robust against pileup. And you also see that the event fraction in a window of plus or minus 1.4 sigma size around the peak is very close to what expected from a perfect Gaussian, 15%. So you see the amount of tail is very small. So this understanding of this simulation of our expectation is based on our present understanding of the detector performance, or the calorimeter performance based on data. And this is summarized in this table here. We have studied the energy response of the calorimeter using various data samples, Z, J psi, W. Today we think we know the energy scale at MZ at a few per mil. We know the linearity between a few GeV and a few hundred GeV at the level of a few per mil. And the constant term of the energy resolution, which is related to the uniformity of the calorimeter, is between 1% in the barrel and 1.7% in the end cap. Here the goal is 0.7%, so there is still some work to do, fortunately. So here you can see the Z2E mass spectrum obtained in the data overlapped with the Monte Carlo. The resolution in the data is 10% worse than in the Monte Carlo, because in this study the Monte Carlo has no constant term. Actually, this is the study we do to deduce the constant term in the data. So then we propagate all this knowledge of electrons to photons, because for X2 gamma gamma we need to know how photon behaves, using the simulation. So if you want to measure the invariant mass of the photon pair, you also need to know the opening angle of the two photons. And so you need to know the position of the primary vertex. However, this is not easy along Z, the beam axis, because the LHC beam spot has a size of 5.6 centimeter. And when you have high pileup, you have many vertices overlapping in this narrow region, and you don't know which one has produced the gamma-gamma pair, given that these are not charged particles. So this is one of the reasons that has pushed us to segment our calorimeter, electromagnetic calorimeter, longitudinally, so to be able to measure the photon direction, and then by extrapolating back to the beam line to measure the Z of the primary vertex. So we have measured this performance with data, for instance, with the photons in the gamma-gamma sample that we select in our gamma-gamma analysis. And here you can see the Z of the vertex reconstructed by the two photons in the event. This is their difference. So first conclusion, the resolution is 1.5 centimeter, a factor of 4 better than the LHC intrinsic beam spot, low enough to make that the contribution of the angular term to the mass resolution is completely negligible. The resolution is dominated by the energy, the mass resolution is dominated by the energy resolution. It is robust against pileup. The two sets of points, open and closed, have been obtained in the first and the last period of operation with different pileup conditions. And so, that's it. Okay, so I mentioned before that another crucial aspects is the capability of rejecting the potentially large background coming from gamma jet and jet production, in which one or both jets fragment into a single hard pi zero and the pi zero fake single photon. This process is of course quite rare. However, look at the cross section, you can see that these processes jet and gamma jet are orders of magnitude larger than the irreducible gamma gamma, let alone the X to gamma gamma signal. This rejection of this background has driven our choice in the early 90s of segmenting the electromagnetic calorimeter in 5 strips in the eta direction, 4.5 millimeter wide, in order to be able to distinguish a single isolated photon from the 2 overlapping photons from a pi zero decay. This is not Monte Carlo, these are 2 events from data. In spite of this choice and this confidence that we'll be able to reject this background, because there are huge uncertainties on this gamma jet and jet cross-section, it was not obvious that we could really suppress this background, which could be a killer for X to gamma gamma, well below the gamma gamma irreducible background, until we have measured it with data. And this has actually happened. So here you can see we using the full data sample selected with the X to gamma gamma analysis. We have estimated its purity by using data-driven technique, and we have measured a purity of the sample at the level of 70%. So out of our gamma gamma samples, 70% are true photons, 20% are gamma jet pairs, where one jet fake photons, and only 5% are jet. So with the detector we are able to keep this background at a manageable level. So results, after all selections, kinematic CAS, gamma identification and gamma isolation, we select in the data 22,000 gamma-gamma candidates. This is their mass spectrum. The spectrum is fit in the 9 different categories with an exponential function to model the background, so no theoretical prediction, no Monte Carlo. The background is determined from the side bands of a possible signal, plus a crystal ball and a Gaussian to simulate a signal. For instance, this is the signal expected for X of mass 120 GeV. So if you subtract from this spectrum the background fit, you get this plot here, where you can see a slight excess here, around 126 GeV, that I'm going to quantify in the next slide. We have carefully considered a huge number of systematic uncertainties, detailed here. They are driven by the gamma identification and mass resolution and background modeling, and we have included them, of course, in our evaluation. So, going to the interpretation of these results, this plot here shows the usual ratio between the extruded cross-section and the standard model cross-section, as you have seen before. You can see that the expected sensitivity here in red is between typically 1.5 and 2 away from the standard model cross-section. However, because of a deficit of data in the gamma-gamma of events, in the gamma-gamma spectrum, in this region here and in this region here, we are actually able to challenge the hints for a possible X signal at LEP. And so we exclude the region between 114 and 114. Sorry. And a couple of GeV here. Now, you clearly see here the excess. Let's quantify it. Let's see, is it consistent? What is the consistency of this excess with the background-only expectation? Well, if you look at the p-value that we've already seen before, the probability, locally, the probability that the background fluctuates up to this level is 2.7 times 10 to the minus 4, or 2.8 sigma. And you can see from this plot that you would expect from a standard model X of a mass, a given mass, here especially 126 GeV, you would expect 1.4 sigma locally. So you see our fluctuation, if it is generally, is a fluctuation upward. So if this is due to a signal, then we are lucky, at least for the time being. If not, if it's just a fluctuation of the background, then it will take a lot of time, a lot of data to kill it. Now, we also have to include, of course, to be serious, we have to include the probability for such an excess to appear anywhere in the investigated mass range, which goes from 110 to 150. This is the so-called look elsewhere effect that you will see many times again in my talk and in Guido's talk also, I'm sure. If you include this look elsewhere effect, this probability goes up to 7% or 1.5 sigma. X to 4 leptons. So Another rare channel, cross-section at the level of a few femtobarn in the low mass region. However, unlike X2WW, one can fully reconstruct the final states starting from the final state. One can fully reconstruct the mass of this object starting from the final state product. And unlike X2 gamma gamma, the signal to background ratio, instead of being at the level of 2%, is at the level of 1. So this is why this channel is called the gold-plated channel for X at the LHC. Now, the main backgrounds are the Z star irreducible background, and at low mass also ZBB bar, Z plus jet, and TT bar with two of the leptons from the decay or big quark jets or from fake light quark jets. And these are suppressed by applying isolation and impact parameter cuts. So in this case, the crucial experimental aspects, for these final states, just an observation of a handful of events clustering around a given mass will be extremely convincing. The problem is that this is a very rare channel, and so it's very crucial to have a high lepton reconstruction identification efficiency down to very low PT, good lepton energy momentum resolution, and also in the low mass region, it's very important to control the reducible background. Again, we cannot rely on Monte Carlo. We have to use data, control samples in the data, but the control samples in the data at this stage suffer from statistics, and so in order to be conservative, we use quite stringent PT cuts on the 4 lepton, 7-7 on the sub-leading and 20-20 on the 2 leading, and we still apply a constraint on the Z mass inside a given window. So I will now spend a few minutes to discuss our lepton performance, especially in the low PT region, which is very crucial for these studies. So we have studied the electron identification efficiency with data using 3 samples, JPSI to E, W nu, and Z to E, in order to be able to adequately cover the PT range from 7 GeV to 50 GeV, and to be able to cross-check and so have more clear understanding of the systematics. You can see that the agreement between Monte Carlo and data is quite good. The agreement among the various samples is also quite good, and the efficiency increases by a few percent when going from 7 GeV to 50 GeV. We have also studied the robustness of this efficiency against pile-up. You can see it here, again, with Z2E events in data and Monte Carlo. You see the efficiency decreases when you increase the number of vertices by up to something like 5% for 20 vertices or so. This is because we did not retune our cuts. However, the important thing to note is that the Monte Carlo is able to track the data extremely well. And so this testifies to the quality of the simulation. Concerning muons, the muon reconstruction efficiency over the region relevant for this analysis is larger than 95%. Also in this case, we have tested the crucial variable for this analysis, like the isolation cut against ZBB bar, TT bar, etc., as a function of pile-up. Is shown here for Z to mu events. We see that it's flat, so it's also well reproduced by Monte Carlo. Another recent achievement that I mentioned at the beginning is that we have new alignment constants, and you see how these new alignment constants have narrowed the Z to mu mass spectrum. The resolution that we get today, these are the red points, is typically 15% better than what we had in spring, and only 6% worse than in the Monte Carlo, which is perfect, no misalignment. So we are very close to ultimate performance. So we put all this experience and all this learning into the simulation, and then the simulation tells us that the Higgs of mass 130 GeV would have this kind of spectrum, a mass resolution about 2 GeV, and the tails outside a plus or minus 2 sigma window will be at the level of 85%. You expect 95% containment, so means the tails at the level of 10%. So these are the results. After kinematic cuts, after impact parameter cuts and isolation, this is the measured 4-lepton mass spectrum over the full investigated mass range, and this is the low mass region. In the total mass region, we observe 71 events with a background expectation of 62 plus or minus 9. And then in the mass region below 180, we observe 80 events with 9 events expected from background. Note that in the region below 114.1 GeV, and this is, remember, is the lower limit of the excluded region by the combination of ATLAS and CMS results based on the summer data, we observed 3 events, these 3 guys here. These events are all clustered in a mass bin of about 1 GeV. We have 2 E to mu events and 1 for muon events. And if you take a region of 10 GeV around 125 GeV, so here, we expect similar contribution here from background and signal, 1.5 events each. The background has a typical conservative uncertainty of 40%. But note that the purity of the final states depends very much on the flavor. So the signal to background ratio is typically 2 for 4 muons final states, going down to 30% for 4 electrons. And also the background composition changes. 4 muon final states are dominated by the reducible Z star, whereas 4 electron final states receive an important component also from fakes, from Z plus jets. So this is one of these 2 events. It's a 4 muon events which shows 4 muons of IPT, 3 of them in the central region, 1 of them is forward, and the largest invariant mass is very close to the Z mass, and the other mass is off shell. And this is one of our 2E to mu event. It's a spectacular event. It contains 4 leptons of large PT. All of them are central. All of them come from the primary vertex. They are really impact parameter close to 0 within the resolution. And you can see that these events, by the way, overlap with another 9 vertices coming from pileup. The photons, the 2 electrons pass tight identification cuts, tighter than those that we require in this analysis. They are beautiful. They are completely isolated. There is no photon around. They are very, very nice. The largest invariant mass is a bit of shell, as expected. So we have spent a lot of time also to understand the reducible background selecting carefully a data sample, controlled data sample. I will leave this to question and move to the interpretation and to the results. So this is, again, the excluded cross-section in the low mass region and in the large mass region. An important thing to note is that with this channel, we are able to extend the exclusion, the combined exclusion ATLAS plus CMS from 141 GeV, was the lower limit, you remember, to 135. So if you take X2 gamma gamma and X2 4 leptons together, alone with 5 inverse Ventova, we have been able to restrict the most likely region, a 95% confidence level, in a window of 20 GeV between 115 and 135. The consistency of the data with the background only expectation is shown in the p-value plot, as usual. You can see that there are 3 fluctuations over the full mass range. They are at masses of 125, I already discussed this, 244 and 500. The local significance is very similar in the 3 cases, 2 sigma or so, which is, by the way, also what is expected locally from the standard model. And of course, the 3 events I showed before for me are quite intriguing. But clearly, when you include the look elsewhere effect, then this very small local significances vanish completely. So now we put together all channels, almost at the end, except X2BB bar. And here you can see the exclusion over the full mass range and expanded in the low mass region. In the high mass region, we are not able to improve much on the ATLAS plus CMS combination because we did not update our high mass channels. And also there, in any case, most of this region is already excluded to a certain degree. Of course, one can always improve the confidence level. But in the low mass region, you can see that we are progressing compared to what LEP was telling us 10 minutes ago and the combination of ATLAS and CMS 2 months ago. So you see that we have been able to restrict the most likely region at the 95% confidence level between 115.5 GeV and 131 GeV. This region cannot be excluded because there is an excess. So what is the compatibility then of this combined constraint with the background only expectation? If you look at the p-value, you see, zoom here, the largest deviation at 125, 126 GeV, and this is an expanded view of the low mass region with the total and the contribution of the various channels. The maximum deviation is observed for a mass of 126 GeV, and the local probability that the background fluctuates up to give us this excess is 1.9 times 10 to the minus 4, or an excess of 3.6 sigma, to which contributes gamma gamma with 2.8 sigma, driving the excess, X2 for lepton with 2.1 sigma, and X2 to WW L nu with 1.4 sigma. These plots also show the dashed line, the expected deviation from the background only expectation of a standard model Higgs of mass 126 GeV in this point here. And you can see the deviation local is 2.4 sigma. So we, as noticed already before, we have a fluctuation up if this is a signal. Also, if it is background, it's a fluctuation up, of course. In the case of the standard model, the expectation is 1.4 sigma, equally per channel, essentially. If we now look again at include the look elsewhere effect, then this p-value goes up from 1.9 10 to the minus 4 to about 1%, and this significance, this local significance, goes down to about 2.3 sigma. So the question is, what is the compatibility of what we observe with the strength of a standard model Higgs signal? Well, the answer was already in the previous slide, but it's also shown here. You have seen that this is the ratio between the best strength that we fit in our data and the standard model strength, and you see that in X2 gamma gamma we have a fluctuation up if this is due to a X2 gamma gamma signal, whereas in the other channels and in the combination we are in agreement with the standard model Higgs strength within 1 sigma. So what's next? Well, first of all, we are going to improve our analysis sensitivities by updating to full luminosity the other channel, X2WW, X2BB bar, and X2 tau tau. And we are also going to try to increase the acceptance at low masses, for instance, for X2 for leptons, by relaxing kinematic cuts, for instance, the lepton PT on the ZMAS window, now that we have a better understanding of the reducible backgrounds. And we will also, we also started to investigate multivariate techniques, more exclusive final states, additional discriminating variables, etc. We know very well from the Tevatron, and this is one of the numerous lessons that we got from CDF and D0, how much better than expectation the experiments can do when they have a lot of data and a lot of ingenuity, and this is demonstrated by the outstanding achievements of the Tevatron in Higgs searches. Then, at some point, we are going to combine with CMS. This is being discussed. And, of course, we need more data in 2012. So the magic number is 20 inverse femtobar per experiment. Okay? So this 20 inverse femtobar per experiment will allow Atlas alone to establish a sigma, so to discover a Higgs at a mass of 125 GeV if the fluctuations we see are really genuine at the level of 5 sigma. If, on the other hand, the Higgs is not there, this luminosity will allow Atlas and CMS together to discover it down to 116 GeV or so. So I'm coming to my conclusion. I think it has been a wonderful year for the LHC and Atlas, and I guess also for CMS and the other experiments. So thanks again to the LHC. We'll see, we don't know. Concerning, well, I would like to stress that Atlas is a very broad physics program, which has been also documented in, as of today, I think 90 papers submitted for publication. But in particular, you are interested in the conclusion on Higgs searches. So one box to conclude, we have looked for a standard model Higgs boson over the mass range between 110 and 600 GeV in 11 distinct channels, and using up to 4.9 inverse femtobar of integrated luminosity. And we have been able to restrict the most likely mass region at the 95% confidence level to a range of about 15 GeV, between under 15.5 and under 31 GeV. We observe an excess of events around Higgs mass of 126 GeV, with a local significance of 3.6 sigma, to which contribute gamma-gamma final states with 2.8 sigma, 4 leptons with 2.1 sigma, and 2 lepton neutrinos with 1.4 sigma. The standard model Higgs expectation locally at the same place is 2.4 sigma, so the observed excess is compatible with this expectation within +1 sigma. This global significance, when taking into account the look elsewhere effect, decreases to 2.3 sigma. I think it will be extremely kind of the Higgs boson to be here. No, I mean, it's not any mass. If the Higgs is here, then it will be accessible to a DLHC in gamma-gamma for lepton, to lepton neutrinos, BB bar, tau-tau, so we can observe it and start to do very good measurements, okay, of these final states. And of course, there are also implications for the future that are not, of course, the subject of this seminar. But it's too early to draw definite conclusion. More studies and more data are needed. But we have built, I think, we believe we have built solid foundation for the exciting months to come. And I don't know what the conclusion will be eventually, but I think the fact that we are here today, as the DG said, to discuss these beautiful results testifies to the outstanding efforts of the LHC and experiments teams, and to the, I would say, dedication and enthusiasm of the whole community. In particular, I would like to mention the young people. And I think this is something really extraordinary, and I think we can be all proud of this. Thank you.
I'll try. First of all, I have to not to despair. Secrets there.
Escape.
Yeah, but I don't have the keyboard. Keyboard. First of all, search the keyboard, which is necessary. Escape. There is no keyboard, so I can do miracles, but not to materialize the keyboard. Yeah.
I was nearly there. Okay.
Close to that.
Take his ball.
Yeah. Yes. Okay, good afternoon. It is a privilege for me to show the CMS results, the updated results on the Standard Model Higgs. I open with this beautiful event display with two isolated photons. And I speak on behalf of the CMS Collaboration, which is a wide collaboration, producing a huge effort in building a beautiful detector, operating it, and now trying to understand the data. The outline of my talk is a short introduction. Then I'll try to describe you the searches for the Higgs boson in the high mass region. My job is a bit tougher because I will describe the many channels, not only the low mass region, which is more interesting, but also the high mass region. Then I concentrate the effort on the low mass region and combination of the searches and conclusion. I don't want to spend time in the Standard Model Higgs boson, but I want to highlight this point. Yes,
This is why you have the time.
I go this way. Yeah. I'll present preliminary results on our exploration up to 600 GeV, but clearly I will devote special attention to the low mass region. I want to highlight this Standard Model Higgs production, not to repeat things that have been already said, but to highlight the point that despite the fact that gluon fusion is by far the dominating production mechanism, VBF and VH are useful because sometimes they give better sensitivity. So we will see some of these production mechanisms in the following. I want to start with the challenge. Those are plots produced by CMS in October 2010, a year ago. It looked like 20 years ago, if I go back in time in memory. At that time, we were dreaming of having something like 5 inverse femtobarn. I remember when I was discussing this with Rolf or Steve, they were really, considering this absolutely impossible to achieve. But anyway, we're preparing our efforts in this direction. And here you see on the left-hand side the sensitivity. Putting together all channels with 5 inverse femtobarn, we could reach, take a look to the black curve, sensitivity beyond 1 everywhere in the full mass region. Ideal case to look for a new particle. First of all, you have to have the sensitivity. If you don't have the sensitivity, you will not be able to say something really solid. And secondly, if you are in these conditions and you get 5 inverse femtobarn, then you see, depending on the mass, the significance of the observation. And this is challenging because take a look to if the standard model exists and it is in the low mass region here, this is 120, 130, you shouldn't dream of having 3, 4, 5 sigma signals everywhere. This is not the case. You have for each individual channel a small excess. And you put everything together and you get 2, 3, 2, 4. This is the name of the game. This is why every single channel is important, particularly in the low mass region, because it adds something and gives you additional consistency checks. And then, clearly, what you need data. Data came, and this was very successful. At the end of October, we have collected something like 5.2 inverse femtobarn, delivered more than 5.7, so really fantastic performance. And the detector was in an excellent shape. The average fraction of operational channel was higher than 98.5%. I will show results in this seminar using a large fraction of the full data set, 4.7, 4.6. This is the certified amount, which is outstanding. And luminosity is determined today with an uncertainty of 4.5%. I remind you that these data were collected up to 6 weeks ago. Just to give you an idea of the challenge of how complex was the work done by hundreds of people in a very short amount of time. I cannot enter into details, but I want just to flash you that the second thing you need, once you have the data, you need to have the tools, the physics tools. You need to understand very well what you are using to identify, first of all, the background components, and later, eventually, the possible signal components. And these tools, there are plenty of these results. I cannot go through them, but just to give an example of the advancement and sophistication of some of these tools. This is the tau efficiency that we can now measure with tag and probe, and we measure to be 6%, which is a result that is outstanding. A few years backward was considered absolutely impossible in LHC to achieve this kind of numbers. Here you see the bit tagging efficiency, again, in different pile-up conditions, up to 500 GeV. You see bit tagging efficiency measured to 10% in this condition. And again, gamma plus jet calibration in pile-up conditions up to many hundred, 500 GeV again. And here is an important plot. Fabiola showed an equivalent one for Atlas, is the electron ID efficiency at the very low PT. The Higgs boson decay into 4 leptons in the golden channel has the nasty attitude to decay to sometimes to very low PT electrons or muons. And you have to be really very well equipped to be able to reconstruct them, because if you miss 1 over the 4, you're lost. You don't have the event. So every GeV you gain in this region is relevant, is important. This is why we did a lot of effort in trying to reduce at the best this PT cut in the electrons in this case, or in the muons in other similar cases. Then you need to understand the background, and this is again a similar plot to the one that Fabiola showed. W and Z plus jets, because they come again very often, they are not alone, they come together with something which creates additional problems in trying to understand what is happening there, up to the very small cross-section of the diboson, which is basically, if you look for an X, you look for a diboson-like events at the end of the day. You look for WW, you look for WW, ZZ, so the dibosons are the natural, irreducible background to these searches. If you are not able to measure the cross-section of diboson, better you forget to look for the Higgs boson. Here is a summary of the decay modes, and this is the list of the channels I'm going to describe. This is a challenge for me, because I will not be able to describe details of each individual channel, because I have to explain you 8 independent channels that we have been able to understand in time to be shown in this, at this seminar. And you see X to gamma gamma, BB, tau tau, WW to lepton to neutrino, ZZ for lepton. The yellow ones are the 5 channels that are mostly used. They're not only used there, but mostly used for the low mass region, so they're very relevant, plus the 3 other channels that uses the I cross-section, the I branching ratio of the Z into jet and invisible, plus there is a nice channel with tau that we use basically for the high mass region. And here you see the documents. They are public, so you can have details. If you want really to understand some of these details, take a look to these documents. They are available, and they contain much more information with respect to what I will be able today to tell you. I want to highlight another point which is important, that not all channels are equal. They have different weights. Not only the sensitivity is important, but also the resolution, because there are channels that produce a sort of, in the presence of a signal, produce a sort of blanket on your limits, and you understand that there is something happening, but you don't understand exactly where, while there are channels which have a very nice resolution, in particular the X to gamma gamma and the XZZ in 4 leptons. We are talking of 1, 2, 3% resolution. That means that if something happening in a particular region, you're able to understand, to localize an excess in this particular region. And once you look for coincidence between 2 high resolution channels, then you are in a very interesting region. Okay? I'm happy to tell you that all 8 analyses yielded the preliminary results that has been scrutinized enough to be shown today. Are preliminary results, they're not final results. There will be more complete and fully understood result coming at the time of the publication within a few weeks, maybe end of January, beginning of February. But as of today, this is already an excellent starting point. And all 8 channels contributed to the CMS combination, which is documented in this document. So if you want to take a look, you can download it and read it. I start with the high mass Higgs in invisible Z, 1 Z, 2 leptons, we use to tag and to trigger. We ask also some boost, 55 GeV, and then we look for what is recoiling against, and if there is not visible energy there, this is something interesting. The challenge here is, clearly we can use the transverse mass because we are looking for objects which are very heavy, but the challenge is to get rid of the background. And in CMS we use, it's like a must. If you want to address this kind of analysis, it's better that you convince the collaboration that you have understood using data-driven methods your background. We don't believe really to people coming up with only Monte Carlo studies, unless there are really very detailed studies on very small corners of the events for which we don't have enough information from the data. This is an example of this. For example, in this kind of search, Z plus jet is an important source of background. And again, you don't have enough data, then you have to use other data, for example, gamma plus jet that you have in abundance. And then once you have understood very well this kind of background, then you are ready to start the search. And this is what you see here in this case, where you see that there is a very good understanding of this kind of background that allows us to move ahead. And this is the kind of data, are examples, data that you are looking at. Looking at the shape, if there is a heavy object with a transverse mass of 200, 300, 400 GeV, you see a change of shape or a small excess in a particular window. So we make the hypothesis of the Higgs boson presence at 300, 400 GeV, and we look if there is an excess which is compatible with the presence of this signal. And since we don't see, let's say, significant excesses hinting that there is something happening, we put limits. And usually, you will see several times that we used analysis, cut-based. We know very well what is happening. And then we try to push using the shape, using sometimes multivariate analysis, boosted decision tree, things that are using the information in a bit more aggressive way, such that we gain something in sensitivity. But we always control that everything is sound using the cut-based analysis that is somehow conservative in some aspects. And so we are able, with this channel alone, to exclude in the range 270, 440, which is already a good starting point. Another channel which has a big role in the high mass region is the ZZ, with, again, 2Z going to 2 electrons or 2 leptons in general, and 2 going to 2 jets. Again, quite a significant branching ratio. Then, again, we have major backgrounds here, again, Z plus jet, TT bar. And we use to discriminate basically the fact that the Higgs, if it exists, is a scalar. So there are topological and angular discriminants that can be used to get rid of the major background. And these are the results. Again, a new fact with respect to what we have already presented. This result, some of this analysis were already presented in the summer conferences, is the fact that this search was extended also to the low mass region. The sensitivity is not large there, but anyway, it helps. So you see here that in this distribution, which is the MZZ invariant mass that you can reconstruct using the 2 jets and the 2 leptons, you see that you look for bumps or deviations at a point that could be consistent to the presence of the standard model Higgs, high mass of 300-400 GeV. In the low mass, you see something that could happen here. But pay attention to the fact that this yellow excess, signaling the possible presence of a standard model is 5 times the expected. So you have really to look to very tiny signals. In the low mass, the life is very tough. Anyway, you are able to produce in the high mass. The sensitivity is important. You see, you touch 1 in this region, and it is between 3 and 4 in the entire range. In the low mass, there is an interesting region of sensitivity. Unfortunately, in the very low mass end, the sensitivity goes very high, is rocketing. So it helps a bit, but is not the key component. And to complete the study in high mass, we did also this one. Is a channel in which we ask basically 1 Z going into electrons and muons, and the other Z going to tau. And this is due to the good understanding of the tau as an object that we have achieved using data collected so far. And you see basically that this is completely different situation. These are the data collected. You look for a handful of events, but it's very clear. So clearly, it is somehow complementary with respect to the approach that we are using in other cases. And you see the sensitivity is not bad at all. You see here, this will be the appearance, again, of a standard model Higgs, 200 GeV, 400 GeV. So we take clearly a very small amount of events, but they are very clear, very clean, and then you look for possible clustering of these events in a particular region. Today, this channel is not really, at the striking edge, but it is important to have it and to continue with additional statistics to produce results. And these are the results produced again in the lab. We see nothing unexpected. Basically, 10.2 were the number of events expected, and 10 we observed. So we are basically within standard model expectations. And then I come to the channels that play a role in the low mass region. Actually, this WW to lepton to neutrino is a sort of workhorse, helps everywhere. Helps from, say, 115 up to the highest mass. It has been described already by Fabiola, so I don't want to enter into details. Just to remind you to interpret better the plots that I'm going to show. We have to fight against the non-resonant background, which is WW. WW are produced dibosons, and we have to get rid of them and try to disentangle a possible excess in this channel from the wide WW background. And what we use, basically, we use the angle between the leptons. Due to the scalar property of the Higgs boson, this angle is small. The leptons are not emitted back-to-back, basically. They are emitted at a small angle. The invariant mass of the 2 leptons cannot be too high, so again, we go into this direction. And then the transverse mass is another tool that we use. Playing these tools, again, you can use this tool in different ways, using the cut-based approach, which is the one that we use anyway as a baseline, or try to put together these 3 tools plus additional information in a multivariate analysis. And this we do. We have done both. We have basically gone through both approaches. There has been a lot of progress in this result. We presented preliminary results on this channel in the summer conferences, but people continue to produce new ideas. And here is a list of some of the new ideas that have been produced, and each one of these adds a small amount of sensitivity. But really, this is an incredibly important effort. Each 1% progress in the sensitivity is needed, is helpful, it helps. And so people are really encouraged to develop and deploy continuously new ideas in this effort. In particular, clearly now that we have established somehow this kind of analysis since a while, we feel confident to move ahead from the cut-based and use also multivariate analysis. We continue to cross-check continuously what is happening. For example, in the multivariate analysis, sometimes we use only one variable, and we check if the variable and the result we obtain is understood. It's a way in which you get confidence on the use of modern tools like the multivariate analysis. This is the result on cut-based. Again, this is the way in which WW selection, you start with there, and then at a certain moment, you increase the cut. You see the cuts are delta phi, the two leptons. You remember I was mentioning them before, MT, ML, M, the two leptons. I mean, this is the region in which, if you see an excess, is the hint that there is something happening. But it's very important. Before going there, you should prove ourselves and that you are able to understand this region. Otherwise, it makes no sense to claim that there is something happening there. And since basically data describes well the predicted background, we can produce limits again, and you see that in this you start seeing something. Because we expected to be able to exclude. The sensitivity here is absolutely outstanding, is below 1, even in the very low mass region. And we expected to be able to exclude up to 129, while we had not been able to exclude below 132, because you see there is some green. Some green means that there is an excess, maybe a sigma excess, a small excess, but there is something happening there. Then we do it a similar exercise again using boosted decision tree again. And now we use a variable that is not know exactly what it contains, but assume that it contains a mixture of the previous variables. So at the end of the day, the message is very similar. And you see that we use different category, 0 jet, opposite flavor, 1 jet, same flavor, opposite flavor, etc., etc. And there you see now 1 times the standard model at 130. What you look for a few bins in the region in which you expect to look for something that could be off. We are not looking of big discrepancy, just 1 sigma effect is important to look for something interesting happening there. And this is important as a cross-check to see that, for example, that we are, again, with boosted decision tree, the sensitivity is a bit better, and actually you see the expected range is a bit better, 127. We gain something, we go lower. But the observed range, again, is 129. We cannot go beyond this, again, because there is a small excess, which prevents us to really close up to the limit, okay? In the low mass Higgs search, was mentioned already by Fabiola, the Higgs to tau is another important channel. Again, the tau, we consider the tau a physics tool that we master quite well, and we use it extensively in CMS. This is an example of a few categories that we are using. We're using 0 or 1 jet, but we use also the boosted Higgs with 1 jet PT very high, and then also the VBF, vector boson fusion, that you select requiring 2 jets in the very forward with the rapidity gap larger than 4. So you have 2 jets, and then you look basically in the central region, what happens there. Clearly, you ask for masses that are quite significant in this jet, and then you look for different tau decay modes. You have the tau decay in hadronic 1 and with the mu on the other one. Hadronic 1, the mu on the other, electron the other one, this is a mistake, sorry, and then muon plus electrons. Here you see the categories. You see that there are different sensitivity. The injection of a signal 5 times the standard model, 120, is not visible here. You see it's buried here. Here is barely visible. You should really magnify the plot if you want to see something. But here in the VBF, you see that there is something. As I said, this dotted line could be the kind of excess that you would expect if a 5 times signal strength, the standard model 120, would appear. So these are basically at the end what you do in going through. This is the sum of the category. Then you go channel by channel because you might have fluctuation in one channel. So you shouldn't pretend to see everything in the overlap of the categories. And you see that there are actually a few, some hint, I would say, not more than that, that the data tends to be a bit higher with respect to the expectations for the VBF categories in this region. This particularly are the T mu and T hadron, T electron and T hadron. And then you produce the limit plot, and you see that in this region, now we are looking really in the region which is interesting, not yet excluded. In this region, the X to tau tau show you that there is an excess. Again, the excess is very mild. We are talking of 1 sigma or so. And the excess, as I was alluding to you before, is sort of a blanket. So there is not a particular mass region in which you see a bump. You see a sort of a blanket covering many tens of GeV. Similar approach, or if you wish, a complementary approach was chosen again in the low mass region, looking for X to BB. Very challenging. We are not able to address the gluon X to BB because basically modes are overwhelmed by an enormous QCD background, many order of magnitudes. Is basically hopeless. What we do basically, we look for association production. I remember that I mentioned at the beginning. So we look for a vector boson produced in association with the Higgs boson. We pay a huge price in terms of reduction of the cross section, but the signal to background ratio improves. Still is very tough, but improves. This we can try, and then you see that we ask to try to gain something. Also, we ask for a very highly boosted W and Z. You see 100, 160 GeV. You see from here, no? This is an invisible, let's say, recoiling against 2BB. So we look really to something very striking on one side that will allow us to understand better if the 2B jets, which are B-tagged by our B-tagging algorithms, if they could be considered possible events interesting for this. Again, 5 sub-channels. Take a look. So I mentioned 8 independent searches, but each independent search should be multiplied by a certain number of channels. The number will become really impressive. You see the Z to 2 leptons, muon and electrons, the W muon and electrons, the Z invisible, etc., etc. Again, here, data-driven methods to control the background is the only protection. Again, here, you see what you are looking for. You see one being a bit off from the distribution in the region that is compatible with the presence of something happening. This is the name of the game. And then you produce, again, with the single variable, which you know very well, the MJJ, so the mass of the object which is produced, and the boosted decision tree, that again you see that in the low mass region, 110, 135, there are more events than expected. We observe a bit more events with respect to what we expected. However, again, the resolution of this channel is poor, so you don't see any peak. You see just an overall slight excess. Then we come to the channels that are complementary to this, because they have very good resolution. The golden one is the ZZ for leptons. We had, you see the beautiful, what you are looking is, Fabiola mentioned already, 4 isolated leptons having the same vertex. So this is the name of the game. So there should be nothing around the leptons. They should be well reconstructed. They should belong to the same vertex independently from the pile-up condition, etc., etc. And here again, the name of the game is to be able to reduce, as I was mentioning already, the PT cut. We use 5 GeV for muons. We are able to do it through tag and probe with Z, and 7 GeV for electrons. But then we discovered after lepton photon that we could improve a bit more again. And here you see the improvement in sensitivity that we have achieved, basically reducing the cut on the mass of the Z prime, the first Z. That would be interesting. The mass of the first Z and reducing a bit the request of the mass of the second Z. There is something behind this. Fabio knows. Reducing, you see the MZ1 cut from 60 to 50. You see here in this region, you gain some possible signal. The same is true if you reduce MZ2 from 20 to 12. You see that we really try to increase, again, bit and pieces of the efficiency that will translate into increased sensitivity. And this is then are the results that we obtain in the full mass range. And you see that we don't observe any excess in the full mass range. Above 100 GeV, we expect a 67 plus minus 6, and we observe 72. But if we zoom in the low mass region, and this is exactly the most interesting region, those are the events that we see. And the first message is basically that we observed 13 events while we expected 9.5 plus minus 1.3. So this starts to become interesting. Again, nothing striking because we are talking of small numbers, but clearly there is some attention there. And you see also the distribution of the events. Overlaid, you see the signal, Higgs boson signal hypothesis. So I try to guide you in the interpretation. 140 is a region already excluded. And you see, we have 2-3 events there. That could be candidate, but we would expect maybe 8. So clearly the signal strength there is not very high. In the very low end, you see 119, 20. This will be 1-2 events, and we have 2-3. So this could be a region to be followed, although a bit high, a bit on the high side with respect to the expectation. And 125, you see that we have 2 events, and basically we expected 2-3. So we are basically in the same ballpark. So in this region, 140 I would consider less interesting. This region, 120, 25 seems to be interesting. However, we put limits. Again, the ZZ is a very powerful channel and is able to put limits all over. And again, you see in the low mass region, we exclude 134, 158, and the intermediate 180, 300, high 340, 460. And you take a look here. This is interesting, the zoom, because this region is very interesting. However, we should be also aware that you see that the sensitivity, recommendation, don't observe the solid line, the observed one. Look always at the dotted one. It's much more important, the dotted one, than the solid one. Because only if the dotted one is in the right region, then you can believe the observed one, right? If you don't have enough sensitivity, if you have an excess, makes no, it's not interesting. So this region is very interesting. I should be careful here. Here you see at 150, we go 5, 6, 7. So clearly we don't have the same sensitivity. However, it's interesting to note that we have an excess. ZZ definitely gives a similar hint to what we have seen so far. There is an excess in the low mass region, and then we'll understand better what is the meaning of this excess. And then we come to gamma-gamma. The gamma-gamma is, again, a beautiful signature, 2 energetic isolated gamma, and we search for a narrow peak or a narrow mass excess over a smoothly falling background. And here you see the challenge is basically the vertexing with the pile-up, the calibration and transparency correction for the crystal for us. We have a beautiful crystal calorimetry, but if you want really to exploit the best its performance, we have to do a lot of work. This was known since ages, but clearly it is a matter of fact. Nothing comes for free. If you want to go beyond 1 GeV or so, then life becomes really very tough. But anyway, we are making a lot of progress there, and you will see some of the results coming already from the progress achieved in the last few months. These are the improvements of the analysis that we have been done with respect to the results shown in the summer conferences. We have improved the vertex identification, again, gaining 3% and being somehow neutral with respect to the pile-up conditions, or mitigating the impact of the pile-up conditions. We improved the energy resolution. And we have changed the categories. We were using 8 categories, now we use 4 categories. We want to use at the best the fact that we have a region, the barrel, which has much better resolution, and by the way, is also the region in which a large fraction of the signal goes, and we want to protect it, and so having a complete picture, summing together everything does not give you the best performance. At the end, we did a huge amount of effort also to parameterize the background shape. Here is an example of the improvements in vertex finding efficiency, where you see that basically in the different periods of the data taking, the vertex efficiency was somehow recovered at a level that is considered reasonable. We lost something, but not significant, with marginal impact on the performance. And this was done again using a BDT and training it using input variables, the track momentum, the photokinematics, such that the vertex assignment is better understood. Again, it's a continuous struggle. The machine gives us higher pile-up, and we lose somehow the performance, and then some of our brilliant students come up with a new idea and brings up the performance again. This has been the story of the entire year in many aspects. This is one of them. This is another challenging area, a key strategic area for the discovery of the standard model Higgs boson in Higgs to gamma-gamma whenever it will happen. We went through a comprehensive energy resolution studies. What we could do, we could use the Z to EE, the W in electrons, using E over P as a cross-check. We used the pi0 for the intercalibration, and then we used the laser to check the transparency correction, because our crystals lose a bit of transparency. You can see here in the barrel, this is 1, this is 97, so 2-3% over the year. If you don't correct, you lose resolution. But if you correct, if you're able to understand the laser response and to model it, then you're able to bring back, you see the E over P that in principle should have fallen this curve, back to this fantastic performance. RMS is 0.14%. So we know the energy scale for W and Z for the entire year at the level of 0.1 GeV. This is the thing that I was alluding to before. A lot of work, which is paying off, but you have to really understand all possible details. And again, here you see in this plot, if you don't do this job, what happens? You see the blue curve is the Z to EE in the barrel if you don't do anything. And then you go for the intercalibration, pi0 and W in U, and you see that you gain something in the width, and also the peak position moves in the right direction. But then only once you have put together everything, including the correction for the transparency, you are able to recover, let's say, performance, which are excellent. Yeah. Once you do it, then you look at the data, again, in different categories. This is the sum of all categories, not used the information is extracted from each individual category's fit. And what you see here, be careful. Don't expect to see this kind of signal in the data, because this is 5 times. Fabiola was probably wiser than me, presented the 1 times, which is less fancy signal. It's really something very small. And then whenever these numbers have a huge statistic, you see, these are hundreds of events. Each beam has many hundreds of events. So the statistical error is very small there. So each fluctuation of a couple of beams, 1 sigma away from the background fit, has a weight. So you shouldn't, again, dream of having there a huge peak, and then that's it. No, it is a pain. You have to understand very well the effect of the background, and you have to go through this, and then you discover, then you are able to put in limits that there is, in correspondence of these small deviations of beams from the best fit of the background, you discover that there are fluctuations, excesses in the limit curve. This is 124, this is 137, 144. It's important that we use to fit the background. We did a huge amount of study, and we decided to use the most conservative approach, to use a function that does not bias the signal and the possible, let's say, excessive one you should see. Although this function, which is conservative in terms of introducing bias, let's say, brings the sensitivity a bit down. Then I come to the combination. I hope to be able to do it quickly, although it is an interesting part. First of all, the sensitivity. This is the expected sensitivity we have achieved. Basically, today CMS is the most sensitive experiment in this area. It is more sensitive than the Tevatron experiments together, with 8 or 10 inverse femtoband collected. In the full mass range, we are below 1 or very close to 1 from, you see here, 117 actually. I'm struggling to get another couple of GeV here. This is the blue dotted curve. And basically, from this respect, we met the expectation. So now we can start say, okay, the sensitivity is below 1 times the standard model. So we can take a look to the data. And what the data tell us is summarized here in the CLS. In the full mass range, this is 90, 95, 99% confidence exclusion, confidence of the CL. And you see the zoom in the low mass region. So again, the expected was 117, 543, a 95% confidence level, and we observed 127, 600. Why we cannot go below 127? Because of this. At a certain moment, there is boom, something happening there. First information. Second, 99%. 99% is not very much different. It's very steep here. 99% is 128. So really, I mean, there is an excess in the low mass region which prevents CMS to go below 127. This is the entire picture expressed in terms of limits on the ratio sigma over sigma standard model. And you see, again, it's visible, something happening in the low mass region. In general, there is a broad excess here, which has some modulation. This is the freshly squeezed electroweak plots done online. CMS only. In both cases, this is what is left since 3:30 today. These are the limits channel by channel. You have a look in the transparency. And then I spent some time, 5 minutes, I hope, in the zoom in the low mass region. 3. I go. What happens in the low mass region? There is an excess, which is not really, is a modest excess, is not striking, but how it is composed. Then we divided the 5 channels in 2 sets. We put together all the low resolution channel, BB, tau, tau, WW, and the high resolution, for leptons, gamma, gamma. Nicely enough, they have the same sensitivity. Around 25 is 1 and 1. And what you see is there, the interpretation is quite simple. This modest excess that prevents us from excluding the standard model X below 127 is produced by, let's say, a broad excess driven by the low resolution channels, modulated by the high resolution channels. It's very simple understanding. Okay? Then we go for the anatomy of this excess using the local and global p-value. This is what we see in the full mass region and in the low mass region. The maximum local significance is small, 2.6 sigma. And if we include Lucas square effect, even in the low mass range, you end up with 1.9 sigma. So this excess has a modest statistical significance and could be reasonably a fluctuation of the background. So there is no discussion on this. But we want to understand better. Data might contain additional information. We don't want to stop here. For example, we ask the question, is the signal strength that we get compatible with the p-value that we might be getting if the standard model Higgs boson would be around? And we compare the entire range. You see that there is no region in which all these p-values are compatible apart the low mass region. And in the low mass region zooming, again, you see that this excess in this region are basically in the same ballpark. So, but take a look to these numbers. If the standard model boson exists, and if we take into account the sensitivity of CMS in this region, we expect to appear as a 2-3 sigma effect, median effect, plus you have to add, let's say, the band there, in the region between 115 and 127. And then I look for the best fit sigma to standard model. You see, again, each one of these points is compatible. Each one of these points in the low mass region, not excluded, is compatible to 1. is a fact that we touch 1 at 124 or a bit lower in this region. And then I take a look quickly to what happens, what is the composition of this effect. This p-value is produced by the gamma-gamma, while this fluctuation has no gamma-gamma. There is a deficit here. It's another piece of information. The gamma-gamma, we have additional information in the gamma-gamma because we have categories, and some categories are very clean and powerful, and others are they bring less information. And you see, first of all, what we see is a bit higher with respect to the standard model expectation, which is the red p-value here. But it's good that it is produced by 3 categories. Among them are the best categories, the barrel, high, non-converted photons, which is again another piece of information. And the 2 categories are sitting exactly at the signal strength that one would expect from the standard model, which is not happening for all fluctuations. These other fluctuations, you see, are the message here is less clean, is less compatible, I would say, ideally, with the hypothesis that we are seeing something that is really consistent. Yeah. ZZ, what we have in ZZ, this excess here is basically driven by the 3 ZZ immune events sitting on top of each other, 119. Here we have 2 events, 125, plus the gamma-gamma, plus some other channels. Another piece of information. And then we go and we try not only to look for the signal strength, but each individual channel. What each individual channel, is each individual channel signal strength compatible with the presence? Clearly, it's a broad picture. We cannot extract too much from this. But we take a look to the 2 excesses, 119.5, 124, and we see that basically, yes, the average, the median value is around 1. This one has a higher ZZ, the 3 events that I was describing you before, and there is no gamma-gamma, but still is compatible. This one at 124, again, is 1, and all categories participate in a consistent way within 1 sigma. Again, could be simple fluctuation, but is another piece of information that we want to put together. So, I conclude. This is the result that we have got so far. And this is the summary. We have been able to analyze very quickly the full data set, and this in itself is a fantastic result. We expect final results, submission of papers expected around end of January. We have maybe new additional channels, also refined analysis. We have reached the expected sensitivity around or better than 1 times the standard model in the full mass range, 115, 600. We have established new 95% confidence level exclusion limits. We are not able to exclude below 127 because there is a modest excess of events between 115 and 127 that appears quite consistently in all 5 channels that we have studied. The excess is most compatible with the standard model X hypothesis in the vicinity or below 124. But the statistical significance, 2.5 sigma local or 1.9 sigma global, is not large enough to say anything conclusive. As of today, the picture is consistent either with the background fluctuation or the presence of the model Higgs boson, and only refined analysis and new data will be able to give an answer. I want to thank the people of CMS that built, conceived, operated, commissioned the detector, the hundreds of analyzers, software, and computing experts that made possible that we present today these results. Steve, Rolf, Bill, all the LHC team for having delivered to the experiments integrated luminosity exceeding our more optimistic expectation. And let me conclude on a personal note, a person which is very important for me, my father that passed away last Sunday. Many thanks to you.
Okay. Thank you very much to Guido for the CMS presentation. Thank you very much for the CMS experiment, for all these perfect, fantastic results. Thanks to both collaboration for all their efforts. It was not only the LHC team, it's also the experiments team. And I think they really did a great job, really going much beyond also my personal expectations, what we would see at the end of this year. Questions? Remarks? There's one over there.
Go to the microphone.
No, he has one.
So, it's for Atlas. I would like to understand, because I'm looking at the gamma-gamma fit and the use of the exponential to describe the background. This is something, of course, we tried also in CMS, and the choice was not to do that. So I'm asking how confident you are in that, in light of the fact that from QCD studies and exotic studies, we know that there is nothing in QCD which is well modeled by an exponential.
So I don't know if I can put work. Well, I should perhaps put some slides back, but I can. You will find a slide in my spare among the spares. So first of all, we have tried several functions, not only an exponential. We have tried these functions on the gamma-gamma background coming from Monte Carlo, like Presbos, Fox, tried it. And then we have also adopted a conservative estimation of the background by taking as background uncertainty the maximum difference in a bin of 4 GeV between the exponential fit and the prediction of the Monte Carlo generators. And these events are not just fluctuated, when in the likelihood they are added with the same part on this PDF as the signal itself, so that they are de facto subtracted from the signal. And the subtraction is at the level of up to, in some categories, up to 5 events or so for a signal which is expected to be in total 60 events. So we are de facto pushing down the signal by hand subtracting the background. So our treatment of the background is extremely consistent. We have done the same exercise by using different function, Bernstein function, etc., and we get results which are absolutely compatible.
I have a question for CMS. Did you try to extract the 90% exclusion limit for the gamma-gamma? Because I have the feeling that it's a bit close to the Atlas success. So maybe we have to check the calibration of each experiment. This is one point. And then I don't understand the strategy for WW in El Niño. It seems that you are really killing the low mass SIG, say, with the last selection, increasing MLL, increasing PT cut on the leptons. Can you comment on that? For the same flower, of course. Maybe in the opposite flower you can gain anyway. But
yeah. No, but there is no, we are protected against this risk. We use a continuous, let's say, basically 3 approach, if you wish, the cut-based, which stays there, and then the M of the two, the invariant mass of the 2 leptons, and then basically the boosted decision tree, bring it together, everything. So I don't think we have any loss of sensitivity. Actually, we have improved it.
I want to make a question to Atlas, then a general comment. The question is, what is the ultimate scale, energy scale, say, precision on the gamma-gamma? Because you have shown 0.5 GeV for the Z plus a contribution from the linearity. So at the end, what is the ultimate value for the scale at 125 GeV?
The uncertainty on the photon energy scale is small. Already the uncertainty on the electron energy scale, as I mentioned to you, is at the level of a few per mil, 0.5% at the Z peak. Then you have some, of course, larger error when you go down to lower PT, but we are below 1%. When we transfer to gamma-gamma, to the photon, of course, we have to take into account the fact that we use the Monte Carlo to go from electrons to photons, because at the moment we don't have enough statistic of radiative Z decays, for instance. And so in that case, we have varied the material in the Monte Carlo, being quite conservative, and what we get is at the level of a few per mil to 1% maximum in the worst categories. So we are at that level.
Yeah, the other point was, if we sum up, it's not allowed to do, but okay, I do it in my head. Okay, I don't know what you sum up, but it's interesting to understand what the single resolution for the 3 events you have in the Z for leptons.
Well, you have
I know the CMS one.
So yeah, where I showed you the mass resolution for X24 electron and X24 electrons and X24 muons. So the mass resolution is typically at the level of 1.9 GeV for muons and at the level of 2.7 GeV or so for electrons.
Fabiola, in the 4-lepton analysis, below 140 GeV, CMS has 7 events, and you have 3, and they pile up exactly at very close in mass. That looks to me a bit strange, but can happen, obviously. But my question is, how much would your p-value be reduced if you count only 2 out of those 3 events, for example?
So if we have a sigma, well, I remember the sigma better than the p-value, so the total sigma is at the level of 2.1, total significance 2.1 sigma at the moment. If you take one of the events, we go down to 1.5, 1.6. Note that we have more events in that region because we have looser cuts. We have as I mentioned, stricter cuts in the PT of the leptons. We are at 7 GeV also in muons, and also we have the mass window constraint, which is stronger than yours. And it's one of the things that we will relax. But until now, you know, when you relax those cuts, you risk to get in ZBB bar background, Z plus J, so we didn't want to.
Okay, but I mean, at the time of the HCP, the acceptance, I mean, the number of events of Atlas and CMS was not so different. So we have increased a bit our efficiency, but not so large.
I have 2 very short, naive questions from a theorist, but well, let me just first thank you for your very nice Christmas gift, yeah, and I hope that you will not take it back. For Atlas, in fact, you have an exclusion at 115.5 GeV, and this is basically because you have some kind of luck. You got a lucky fluctuation, I guess. Is there a way, in fact, to have some kind of look elsewhere effect for also such statistical fluctuations? In fact, did you just think about it a little bit? And for CMS, another question is that I see that you have excess basically everywhere, in basically all channels between 115 and 135 GeV. Could it be just that you are simply misunderstanding the background and underestimating some of the backgrounds?
Could be, but we should be really very, very precise in misunderstanding the background, which is completely different for all channels. So I cannot exclude, but I will give a very small probability to this hypothesis.
Yeah, so for what concerns this, no, we don't, I mean, as far as I know, I don't have a look as well as effect for the deficit, but perhaps one of my friends, statistics experts, can reply. But you know, again, the important thing is to state what we do is an exclusion 95% confidence level. Okay, so and we always claim that excluding the Higgs boson wherever on a mass, the full mass region, it has to be done at a higher confidence level. So that's why. And I think that I was quite kind to Lev saying that we're just challenging the lab hint and not really.
I have a question to Guido about the very interesting and nice result you showed for the crystal calorimeter recalibration to account for the loss of light of 3%. So 2 questions. One is, by how much has it improved your end cap Higgs to gamma gamma mass resolution? And the second question, did I understand correctly that you claimed you understood the scale to 0.1% in the sense that if we would find a Higgs to gamma gamma around that mass, you would measure its mass to 0.1%?
No, the scale is the different, the EP scale. If you take a look to the plot, which is shown here. I was mentioning this, now it's up. You see, I don't know if you can read it, but this number, the RMS of this E over P, which is stable over the year, this is what I was alluding to. Now, the stability you achieve once you are able to correct for the transparencies, which is really very painful, but it is effective. On the other hand, the barrel, we have made a lot of progress also in the end cap. The progress is not in big jumps. We are talking of 10-15% progress each step of additional understanding. The end cap is still the region in which we need, and we have the possibility to improve a lot. The reason of this is basically that up to now we were limited by this phenomena, basically, the laser transparencies, while now the limitation is the cluster correction and the material distributions in front of the end cap, which is our beautiful tracker, which is fantastic, but has a nasty property that to produce signals needs some cooling pipes, electronics, etc. The average distribution is well understood, but here we are sensitive to each individual feature, and we have to go probably through another iteration of understanding the material with conversion, with interaction, nuclear interaction, as we did for the barrel first, as it happens in all experiments. We first concentrate the effort for the barrel, and then now we have to really tackle very aggressively all the end cap situation. Thank you for asking.
Yeah. I have a question to both speakers on the 4-lepton channel. Can you give us some insight on how final state radiation is taken into account and the kind of systematic uncertainties it introduces to the reconstruction of the invariant mass?
Yeah, I don't know. I don't have the table of the systematics for the going through all systematics for this, but I don't know. Remember the number? Maybe somebody can help me. What is the systematic error assigned to the?
No, we are not using we are not quoting the FSR systematic because we are taking it our analysis is inclusive.
Okay, sorry.
We have an inclusive analysis, so we don't consider the
Chiara, okay, sorry.
The FSR in a separate way.
Okay, thank you.
Similar for us, we use photos, and I don't think that we have any particular contribution from that. Is inclusive, as Chiara said, for CMS.
Okay, since there's no more questions, so let's say final remarks. I think we have seen a fantastic year, as I said at the very beginning, not only from the LHC, but also from the LHC experiments. I find it fantastic that we have the first results on the search for the Higgs. But keep in mind, these are preliminary results. And keep in mind, we are talking about small numbers. And keep in mind that we are also running next year. So, in conclusion, the window for the Higgs mass gets smaller and smaller. However, it's still alive. But be careful. It's intriguing hints in several channels, in 2 experiments. But please be prudent. We have not found it yet. We have not excluded it yet. Stay tuned for next year. Thank you very much. Merry Christmas, etc.